Alright, welcome to the last video for chapter 10. Just going to wrap up with a few concluding thoughts. Okay, so I'm going to show you two pinwheels. Just going to recall. I'm going to draw this one really quickly. And it's the same thing that I handed out in class, the same thing that we drew at the beginning, right? We have this pinwheel. I'm going to just give you the very nuts and bolts reactions. HX, right? Might be in different order. Hydrohalogenation, hydration, they kind of go together, right? I think I switched those two left and right. This is a catalyst, sulfuric acid. Here you can add H and OH. Okay, you add water. Both of those go through a carbocation. And then we have two more reactions. We can add Br2 or X2. It can be Cl2. And then we can add Br2 with water, for example. Over here we get BrOH, and over here we get BrBr, right? We said these do not go through a carbocation. Instead, they go through the bromonium. Okay, or a chloronium in the case of chlorine. And then, of course, we have hydroboration, where we talked about BH3, or you could have R groups there, where you're adding H and boron across the double bond. We talked about how you could oxidize that. Again, another mechanism is that you're adding this in a concerted way. And this one we didn't talk about. We mentioned it before, and we'll talk about it in Chapter 12. It's a reduction, so we save it for Chapter 12. But it's got a similar feel to the hydroboration. So those six types of reactions we introduced. And I want to start this one by introducing another pinwheel. And to give you some of this will be review, and then a little bit of looking ahead to Chapter 15. Regioselectivity of alkene addition. So let's look at HBr. That's a hydrohalogenation that we mentioned before. We showed these in class. The bromine is going to add to the more substituted carbocation, and the H is going to be added over there. Okay. Interestingly, you can add HBr, and you can add a radical initiator, heat, and ROOR is a peroxide. We'll go over this in Chapter 15. But again, just a glimpse ahead, we get the opposite regioselectivity, the opposite region. The bromine ends up being on the less substituted carbon. So you get the opposite addition of HBr. Okay, we'll show that's a radical mechanism, very different mechanism. We talked about H2O, H2SO4. So this isn't grouped by mechanism. This is grouped more by differing regioselectivity. So hydration is going to do the same thing that the hydrohalogenation did, is put the electronegative group on the more substituted carbocation. But then hydroboration, the two-step process, R2BH, H2O2, NaOH, hydroboration oxidation, that adds the oxygen at the less substituted carbon. Okay, so if you're kind of tracking, you can see that these two are the opposite regioselectivity of these two over here. Okay, so mechanism is absolutely crucial. Okay, and not so much an opposite regioselectivity, but just to remind you, Br2 will give you something that looks like this. Okay. Whereas Br2H2O gives you something that looks like this. Doesn't matter how you draw that. And so there's rationale for all that. Okay, so those two are not so much regioselectivity, but in any event, all those reactions I just went over quickly are on that handout, and of course we've gone through each of them stepwise. Okay, so if you look at and it's kind of summarized in 10.16c a little bit, at least the hydroboration and the hydration. You can see the opposite nature of those. Okay. The 10.17 is entitled Keeping Track. Oops. keeping track of reactions. Okay. It kind of walks you through substitution. So we saw how Rx can do substitution and elimination. Okay. ROH can also do substitution and elimination. But what do we have to do first? Only when we can convert the OH to OH2 plus, only when it's converted to that and becomes a good leaving group can we do substitution and elimination. And then, of course, in Chapter 10, we've been learning about how alkenes can do addition reactions. So we've covered the big three: substitution, elimination, and addition. Okay, so the key to this really is practice, repetition, repeat again. Okay, over and over and over. Okay, so let's do some retrosynthesis with alkenes, 10.18, to reinforce some of these reactions. Okay. Let's say we wanted to make this dibromide. Okay. Again, we're not giving you stereochemistry. We're not so worried about that at this point. I want you to think about connectivity. So this arrow represents how would you make this. And let's say I gave you a starting material, an alcohol. This is cheap. It's in a bottle, cyclohexanol. So we could come up with a couple ways maybe to make this. All right. And the way to think about this is you can either work backwards or you can work forwards from the starting material. That's a regular arrow. Okay. You could draw a backwards arrow going up. The point is you can. I don't really care if you use backwards arrows. You can use forwards arrows if you want, but the way to think about this is both backward and forward, and then you try to meet in the middle. Okay. So what can we do with alcohols? Well, we can convert that OH to a good leaving group, and then maybe do some substitutions, right, or some eliminations, or things like that. How do we make dibromides? Well, we just went over those. We can make dibromides by using Br2 from an alkene. We can do an addition reaction. So now if we look at this alkene, how do we get from, we've simplified the problem, how do we get to the alkene from the alcohol? So we can keep working backwards and say KO tertbutoxide, potassium tertbutoxide. What would that give us, or what would we start with? You could put a chloride, a bromide, etc. Okay, pick a chloride there. Then we would ask ourselves, how would we get from the alcohol to the chloride? It would be HCl. Okay, there's other ways too. You could convert it to a tosylate first, but then you would need something like some sort of chloride source, and we haven't talked about that as much. Okay, but in any event, you can treat that with HCl. And SOCl2 was the other one that we mentioned in Chapter 9. Okay, so there's multiple ways, and also you can go directly from the alcohol to the alkene. We know how to do that. We could use H2SO4 or PTSA. There's other ways. We could convert it to the tosylate, and then we could eliminate with purity. We could use POCl3. Okay. So the point is, there are lots and lots of ways. POCl3 and purity. Okay. So don't be, when you look at these problems, keep in mind there's lots of ways, and you have to come up with a reasonable approach. So let's do some more. The way to do these is to practice. Okay. Do some more here. Here's a halohydrin. We want to make this from a bromide. Notice there's 4 carbons in the starting material, there's 4 carbons in the product. So, how do we make a halohydrin? Chlorohydrin specifically, Cl2, and water from what? The alkene, right? So the alkene, you can treat that with chlorine rather, and water. Okay. Again, what can we do with bromides? We can treat them with sodium hydroxide to make an alcohol. Okay. So again, you can kind of go in this forward sense if you want. And you could get an alcohol. So, how do we go from this? This question is two sides of the same coin. How do we go from the alcohol to the alkene? It's the same question of how do we work backwards from the alkene. Okay. H2SO4 will give us elimination, or again PTSA, Pocyl 3, pyridine, etc. There's multiple ways. Okay. Again, you could take the bromide and directly treat it with potassium tert-butoxide, right? Let's just draw out that H, alpha, beta, get elimination, and you get the alkene. Okay, so that's a couple different pathways. Okay, let's look at a more complex version, and this will illustrate that the power of working backwards. Okay, so I'm going to give you a pretty complex molecule. We're not worried about stereochemistry at this point. And I'm going to say, how do we work all the way back from methyl cyclohexane? At this point, we haven't talked about the very first reaction, but again, I'm putting a thought in your head about radical chemistry. We'll get to that, okay? But we'll get there in a second. So I'm just going to go through this kind of quickly. I'm going to work backwards, right? R2BH, H2O2, sodium hydroxide, hydroboration, right? Hydroboration from an alkene. And this alkene epoxide, and again, if we kind of track this through, is this gonna line up correctly? Yes. Okay, the more partial positive is going to line up with the partial negative of the H. Okay, so hydroboration, oxidation will give you the oxygen at that position, at the less substituted carbon. So let's keep working backwards. To get a double bond, we might use something like potassium tert-butoxide on this chloride. Notice we haven't done anything with the epoxide yet. There might be, so this chloride now would be our starting material. How might we make the epoxide? Chapter 9, sodium hydride from the alcohol, the halohydrin. Okay, so now we have a dichloride. I switched the Cl and methyl there, but we have a chloride and an OH, right? What happens? The sodium hydride deprotonates. You get an O-, that comes in and does SN2 on the Cl and pushes that out. 3-membered rings are more favored than 4, just FYI. Okay. And then you could use Cl2 from the alkene. So this alkene you could treat with chlorine gas. Nasty stuff, actually. Get the Cl, the chloronium, and then the Cl- pops that open. Okay, I'm going to go this way. You could use sodium hydroxide with this bromide. Okay, we got a secondary bromide, so you certainly could get elimination in a retrosynthesis problem. You can make some assumptions, okay, that you get some product here. Not unreasonable, okay, to think about that. Sodium hydroxide would do SN2 on that bromide and go that direction. Okay. If you wanted to, you could say plus elimination products and separate. Okay, this is a very complex problem. I'm trying to illustrate the power of this. Okay. We're going to see some radical chemistry. So these two reactions we have not seen yet. NBS, we've introduced the reagent, and light would actually give you what's called allylic bromination. Okay, so you have not seen that reaction yet. You can treat an alkene with NBS light and you get a bromide at the allylic position. Okay, don't worry so much about that yet. Running out of room. Again, this is mostly for illustration, but potassium tertbutoxide of the bromide might look something like that. Now we've got a tertiary alkyl bromide. We would eliminate that, right, to form the double bond. And again, another reaction you have not seen yet is Br2 and heat or light. Okay, radical bromination. We're going to get to that in 15. I just want you to see you can take very simple alkanes. Once we learn about radical chemistry, you can functionalize them. You can go through this whole, however we went, this whole pathway to get to this product. Okay, so see that, the power of it. Okay, there are many more cases that we could do. Let's go ahead and do one more with some stereochemistry, just to reiterate that. Just want you to see that we can begin to think about making really complex molecules. So this starting material, let's assume single enantiomer, because I've shown you stereochemistry. We're going to work backwards from a very simple methyl cyclopentane. Again, you can go forward from the starting materials, but as things get more complex, you really can almost only work backwards, at least for a while, until you see something that you can really do something with. Okay, so if we work backwards, we could think, okay, I see this oxygen here, I see this CH3O, and I could maybe use this epoxide. What would happen if I added sodium methoxide? I would get the O minus, just to show you a mechanism here, to come from the back face. Pop that open, you get protonation. You get inversion of stereochemistry, so that would work. So maybe, how do we make an epoxide? We'll talk about more ways in chapter 12. Right now we can think about maybe this chlorohydrin. Chlorohydrins are really useful intermediates. You could treat that with sodium hydride, deprotonate, right, that H, form the O minus, attack the Cl, do SN2 inversion, and get the epoxide. How do you make a chlorohydrin? Chlorine and water, starting from the alkene. If nothing else, these problems help to review. Again, these are complex problems. Okay, alkene, potassium tertbutoxide from the bromide, let's say. Again, so you would eliminate. Again, keep in mind what this is saying with forward reaction. Potassium tertbutoxide, we're treating the bromide, right? And we're eliminating to form that, the double bond. How do you make a bromide? Again, we'll learn about this in chapter 15. Br2 with heat. It's radical functionalization of that CH bond. And we're going to find that you're going to be able to take the most substituted CH bond, break that apart, put a bromine there. All right? So that covers chapter 10, okay? And it's a major chapter. They're all major chapters. Alkene additions, okay? So again, we talked about carbocation intermediates. We talked about bromonium and chloronium types of intermediates towards the dibromide, towards the halohydrin. And then we talked about hydroboration, and in chapter 12, we'll talk about hydrogenation. Okay, so group those mechanisms together. Chapter 11, we're going to talk about alkynes, triple bonds, and we're going to see a lot of the same types of reactions, but we have an extra pi bond that we have to take into account, so we're going to see some different things. So we'll get into chapter 11 next.